Newton's iteration, and that's what we will be looking at in this video. Now, Newton iteration is essentially a numerical way to approximate solutions to any equation fx equals to 0, where f of course has to be a differentiable function, because that's what the formula, you will derive it with me and realize that's a demand for the formula. Now, the idea here, okay, in Newton's iteration is to start with an approximation of the root that we want to find, and then improve the initial approximation by replacing the function f by a linear approximation. So you will see that the knowledge of linear approximation that we have done in previous videos will be very helpful here. Now let's see how this is happening. The iteration to approximate numerically a solution to fx equals to 0 starts with an initial guess. So I will guess some x naught as a solution for a function fx equals to 0. In the case of the function graphed on the right, any function for that matter, say, okay, if this is my function, so I'm just gonna make a guess, and if this is the axis and this is the function going, so say I'm making a guess that my root lies here, and I will draw a tangent here and move. Now, so the guess is that x naught is the root. Now let me take you through an example. The example that I want to take is finding root 5. Okay, root 5, finding root 5. Now root 5 of course is also an answer or root of an equation x square minus 5. So root 5 is essentially, I can write, if x is, okay, if x is root 5, then x square is 5, so x square minus 5 equals to 0. So root 5 essentially solves this equation fx x square equal x square minus 5. So in approximation we saw how to approximate function, right, near a given point by its tangent. So that's the idea that we will be using here. So now we know that root 5 is somewhere in between 2 and 3. Okay, root 5 is definitely somewhere between 2 and 3. So let's just choose to use the linear approximation at, say, x naught equals to 2. Okay, now the function is x square minus 5. So what will be f dash x? 2x. Now linear approximation actually told us that fx near x naught is approximately same as f x naught plus f dash x naught, this is a dash here, into x minus x naught. So let us just apply this knowledge out here. So this is what I will get when I'm taking x naught as 2. So t is 2 square minus 5 plus 2 into 2 whole into x minus 2. Okay, so this gives me 4x minus 9. This gives me 4x minus 9. Okay, now we will then get solution to fx equals to 0. Now I can equate this to 0 and get the solution that x equals to 9 by 4 when my x, this is essentially x1. We took x naught as 2, we found x1 as 9 by 4 or 2.25. Okay, so that's what we mean. Here's a parabola, just see. Okay, so now I've created a tangent out here and I found x1. Okay, so this is the point which is where the graph of fx crosses x-axis, right? The graph of fx crosses x-axis. Now we approximate that point by the point where the tangent line crosses x-axis, because we are saying that fx is an approximation of that tangent line. So we can keep on we can keep on repeating these steps. When we keep on repeating these steps, what will happen? We will come closer to the function. We will come closer to the function. The distance or the error between, there is an error between, there is some gap between the function and tangent, so that will start disappearing as we keep on repeating. Now I can take my new point as x1, which is 2.25, and I can find another linear approximation around that point. I will get 161 by 16, and so on and so forth. You can even find x3 and so on. Now if we call x2 the solution to the function, okay, the solution to the function, or fx1 plus f dash x1 x1 minus, sorry, x minus x1, okay, this will be even better. Okay, we are getting closer and closer to the root. So we could continue this kind of a process. We can continue these steps. So this is the basic idea. Okay, this is the basic idea. Suppose that, you know, suppose that this is some point, okay, which we suspect is near a solution, okay, x naught. Then we can form a linear approximation at that point and solve linear equation instead. Okay, so we can, that's what we have done. So thus we call this point equals to 0. So essentially what are we doing? What we are doing, we are solving this equation. So a generalization, I'm giving you a generalization here. What we have been doing, we have been solving this equation, hence I get my x as x naught. Okay, this x naught from here goes here. What I've just done is I've taken this to one side and x minus x naught to one side, and the functional values to one side. So hence I get my new x as dependent on the previous x. So quoting this as x1, quoting this as x1. So this is my new x is derived from old, new x derived from previous x, okay, and in general we call it the Newton iterations, and the formula for it is that the xn plus 1 will actually equal to the previous xn minus fxn upon f dash xn. Okay, so this is essentially the idea behind Newton's iterations, which is used for a lot of functional equations.